Let's start with AnyLogistics workshop. It will be done mostly by Anatoly, the head of ALX development team, and I'm Timofey Popkov, the director of business development of the company. So this is the agenda for today's workshop. Actually, since last AnyLogic conference, many things were added to AnyLogistics, and certainly this workshop is too short to show you even just half of that. So we decided to focus on the most interesting features from our point of view, and this workshop will be actually around just interconversion feature of AnyLogistics when you may convert this scenario or just a network optimization scenario to the dynamic simulation, and then proceed with a further analysis of the supply chain. So we will start with the network optimization part, doing some supply chain structure optimization, and then continue with the dynamic simulation modeling, estimating some parameters of the supply chain. At the end, if you have time, we will show you some examples of inside four walls modeling with AnyLogistics. So, could you please switch to the next slide? So, this is the problem definition. So, let's say we are going to start selling innovative wireless banana headphones in the United States. So, our addressable market is about 10% of the population. We have 28 possible locations for our distribution centers, and we plan to produce the headphones in Mexico, where there is a key supplier for the components. So the question is, find the supply chain structure. By the way, this is how those headphones look like, and this is just some ideas about the positioning of those wireless banana headphones. So, Anatoly. Yeah.
Yes. Thank you, Timofey. So I will switch to AnyLogistics. Here is how it looks like. And we already have a pre-built scenario which contains all the data regarding demand of our customers, which, as Timofey said, corresponds to population of US cities. We have also like physical transportation layer defined, paths between locations. And we also have flows and storages defined for each location, as well as associated costs. Let me show it, like facility expenses, which are different from facility to facility. Who of you are familiar with network optimization, with linear programming? And who's not? Okay, so probably it makes sense to give a brief explanation how it happens. So when we talk about network optimization, we talk about analytical model, which describes all possible ways how your supply chain could operate. So it defines all possible flows, all possible locations for facilities with specific constraints on throughput, with specific costs. And it also defines demand points. And as a result of optimization, we get optimal solution. So it's the best set of flows and facilities that gives us better objective function value, which in case of network optimization is maximizing profit by default. And of course, this optimal solution should satisfy all the constraints that we put in our model. And another outcome of this optimization is set of different statistics regarding flows, values, storages in each period, costs associated with each specific cost type, like facility expenses, storage expenses, transportation, and so on. So let's get back to the product. And let me run optimization. So as Timothy said, we have 28 points of or potential locations for our sites, and we need to choose best ones. So we've run optimization, and we already have got best proposed structure of our network. And in this case, we see 4 proposed locations. What else I can say regarding network optimization? The objective function is customizable, and by default it contains revenue and all the costs and penalties. But initially it doesn't consider CO2 emission. So my question to this model is, will it change if we consider also CO2 emission? And to test that, I will add this CO2 emission part to the objective. So we have a multiplier here that converts grams to dollars. And I will run network optimization again.
Yeah, I just saw that.
Oh.
Stacker. If you could please switch back to the tables because probably it's possible to see.
So here is.
Yeah, here it is. That's the objective, which is counted as which one?
And some conversion coefficient. So I will run network optimization again. Profit is a little bit lower, which is obvious because we added additional cost, right? Which is cost of CO2 emission. And we see that our network structure indeed changed. Instead of 4 locations, we've got 5. If we explore results of network optimization, we will see all the flows that happen in this model. Yeah. Here there are the flows, their values, and associated parameters and costs. We can also understand how much should we produce and how many raw materials we will consume. And a lot of other statistics and all the objective members as well, summarized to objective value. We can also look at the network structure. So some sites were not used at all. They are switched off. And each location that has been used by optimizer supplies its own set of customers. So we have our network structure. Is it enough to implement that supply chain in real life? Obviously not, because we know values of flows, but we know nothing about kind of operational level, inventory policies. Which inventory policies should we use? What will be parameters of this inventory policy, and so on. So I'd propose to proceed further with exploring this result. And I will go to optimization result, and I will convert it to simulation scenario. I will rename it, and new name will be supply chain implementation.
So what we just did, so we used network optimization to find like the best supply chain configuration, taking into account that our supply chain actually is represented as a set of linear dependencies. So we did not take into account any just actual parameters of that supply chain. So basically what we have now, this is like the plan. And actually the picture which we have here, that's exactly represent actually that once you have a plan, probably there are many ways to do it wrong. And probably very few of them to do it right. And if you are talking about supply chain, about that implementation stage, sometimes you will not be able even to recognize that you did it wrong. You just did something, but you have no idea if you could do it better. So, and that's where dynamic simulation helps a lot, because it allows you to take into account, to consider the characteristics of the actual supply chain, to estimate them, and then deploy those actual characteristics to the real world. So, what we have now the supply chain structure, which we just did on the previous step. So we know how much we are going to produce, we know the flows between the facilities, and now we are going to estimate few metrics like the finances. We want to look at the profit and loss statement. So we want to estimate service level and capacity, for example. Yeah, let's continue.
So as a previous step, I converted result of network optimization to simulation scenario. And that technical part actually is a analytical conversion. So taking into account flows values, demand structure, network structure, it generates proposes inventory policies and their parameters. So at this table, you can see that each facility has its own inventory policy proposed on top of results of network optimization. And let us check how our network behaves in this case. I will go to simulation experiment. By the way, one of the new features is validation. So if you missed something in your scenario or experiment settings that doesn't allow you to run an experiment, a validation part will check all the data, all the parameters, and will give you a suggestion what's wrong. In my case, I have all my supply chain defined by individual headphones units, pieces. And my statistics by default is cubic meters. So validation view suggests me to change it. So I change it to pieces. Other way could be to define a conversion from pieces to cubic meters, but I will stay with just gathering statistics in pieces. And I will run an experiment. So this is dynamic simulation model powered by AnyLogic, and it behaves in model time corresponding to the rules we defined. So each distribution center, for example, has its own behavior inside, like 3 processes. Processing incoming orders, sending outgoing shipments, and processing incoming shipments. Behavior of customers is a little bit easier, smaller, because they just place orders and get shipments. So during the simulation, we gather a lot of statistics, and I will add some of those to the dashboard. I will start with service level. And we see that it's 1, so 100%. I will also add statistics about available inventory on each facility except factory, because it's our main interest. I will make it a line like this. So we can see inventory dynamics on each facility. And the main question for us is, what should be capacity of our facilities? So it also can be measured, and I will use peak capacity statistics for that. Again, I will make it per item, and here it is. After we finished experiment, we can save the results to internal database and explore them further. So now we have like ideal behavior of our supply chain. We see that our service level is 100%, and actually our demand is kind of predefined. It is not stochastic, right? And all the parameters of our inventory policies were proposed based on like average demand, right? So let us check if something will change if we have some variability in our demand. I will make a copy of our scenario. A new name will be implementation stochastic demand. And I will use another AnyLogistix feature, which is partial import. So I will import a scenario, but only demand part of it, and I specify that I put it to existing scenario. So now if we look at the demand, we will see that it's distributed uniformly in some range as it was in initial problem definition. and that range differs from customer to customer. So let's run simulation again, and we'll see whether that change influence our supply chain behavior. Oh yeah, the picture is different, and I don't know whether you can see that or not, but our service level dropped to 96%. Obviously, it might be okay in some cases, but what if that service level doesn't satisfy our needs? What if we need a better service level? What should we do? There are several techniques to adjust inventory policies, and one of them is like safety stock, right? Keeping safety stock for the same inventory policy. And there are like analytical approaches to do that, but they have some limitations on demand distribution, on network structure. It should be done echelon by echelon. And we have another approach in our product. So we use simulation to find proper service level, to find proper safety stock to preserve desired service level. So should we
switch back to the slides? Next one. Yeah. So that's the next problem definition. Now we are going to estimate safety stock. So again, what we have the supply chain structure and already estimated some basic metrics of how our actual supply chain should work, should operate actually. So, and also what we did, we added demand variability into our supply chain. So what we want to do, we want to estimate what should be the safety stock to provide 98% service level. And actually at that stage, we already may think about how to market our product, right? So, yeah, could you please click on that? So we know that actually banana is a very healthy thing, and certainly we may use it to market our wonderful wireless banana headphones. For example, we may run the campaign, just click. We may run the campaign like that, saying that includes like a zero cholesterol, it's fat-free, so it's gluten-free, and so on, and it definitely should work. So that's one of the ideas we have with Anatoly, how we could start with that product. So let's continue with estimating safety stock.
So in safety stock estimation experiment, we have just some of parameters.
Sorry, we didn't show the slide with ideas, sorry.
Oh, really?
Just, yeah, the next one.
Next one?
Yeah, please, yeah. Well, sorry, guys. So
that's... Timofey, let me start the experiment and then you will explain it.
Fine.
So, once again. Here.
Okay, so how does it work? So I actually like it a lot. So because that's completely different approach to estimate safety stock. If you try to calculate that using analytical methods, you always have to do many assumptions. Two of them, for example, you always assume that your demand is normally distributed as well as a lead time. And the second problem, you always have to forecast the demand for each echelon, and you have to do this manually. With the dynamic modeling, that's completely different, because if you already have your supply chain, you actually know how it works, how it operates. You might just run that simulation and see how it works. So, and this is what we do in AnyLogistix. So we have a reordering point, then and so on, we have a reorder up to point. So
I don't know what you did.
yep. So we introduced so-called, how we call that, redundant safety stock. We know in advance that that's much more than you actually need. And if you look at the ideal situation, that will be like that. You will never use this redundant safety stock. But once we introduce variability into the model, we'll get a different picture. For example, like that. And what we do at the end of each simulation run, we just measure how much of that redundant safety stock was required by the model to operate. For example, if you just take into account all those spikes, so then it will be 100% service level. So and so you may just decrease that portion, right? Trying to find the service level we are looking for, maybe 90%, 92%, whatever else. While, by the way, if you are talking about analytical approach, the service level you're estimating, that's always 98% because it should be within those 3 sigmas. So, does it make sense to you? That's just very brief explanation of how it works. Again, we run multiple experiments. We run the same simulation multiple times. At the end of that experiment, we just measure, do the analysis of all the statistics we collected, and analyze the results, which just Anatoly will demo you.
So I ran 5 replications of this experiment, and desired service level was 98% as we agreed. And I hope these 5 replications will be enough in our case. Sometimes you have to increase it depending on variability, network structure, and so on. So as a result, you get statistics by each distribution center, and it shows the histogram of safety stock used in each replication. So what we can do after that, we can again convert result to simulation scenario. So we get the same structure, but our inventory policies are now adjusted. So an experiment proposed safety stock values, which will be enough to support our desired service level. So let us run simulation again, and I will add service level statistics. So the model stopped, and we see that our service level is 98% now. So of course it might be even higher because we use stochastic model, right? And it might happen that you'll get higher service level, but statistically it should be near that point that we specified, 98%. Well, why not? So let me switch to
back to that dynamic simulation. Yeah. So could you please choose another one? You probably so we just when you run that experiment, you define the number of replications to do that number. We just did only 5. That's why we have so just poor, let's say, histogram here. But it's only the more applications you run, the better picture you will have here. So the idea behind that histogram, again, that basically says that, let's say, if you have a safety stock like that, that's 741, then in 100% cases, it will be enough for you to provide the service level you want to. Let's say that that safety stock, which is, I guess, 560, yeah, this one, for example, yeah, this one. This service level will be enough in, I'm sorry, I don't see how many. What's the probability here? That's, yeah, in two cases, yeah, so that's the probability here, this is CDF, that means 60%, basically, yeah, this one. Sorry, 60% here. So, again, simulation experiment is a stochastic one. So, and certainly the more simulation runs you do, the better picture you will have here for each warehouse, for each product you have in your system. And using that histogram, you finally might take a decision what should be the actually the service level you're looking for. So, does it make sense to you? I just explained. Any question on that? Oh, yeah, please.
What about the other parameters that, like your min and max or your reordering point? Are you going to simulate those in conjunction with the safety stock?
You mean min max, you mean the inventory policy or what? So, or
right, regarding to the inventory policy, right now you're simulating the safety stock only, right? So you basically already set your reordering point and the max up to point, right? As you changing those parameters, the safety stock will change too.
Right, but the parameters of inventory policy, min and max, were identified on a previous step when we converted network optimization to simulation. And we actually take into account lead time from supplier and and how often our orders happen, how often our customers order. So taking these two parameters, we identify like periodicity and the actual value of like small s and big S.
Yeah, could you please switch back to the slides? I think it's better to explain there. So this one. So what we have here, so basically that line, yeah, that line, and this green line. So this is ideal inventory policies for which we calculated this small s and big S. So this is ideal. So it works perfectly if there is no any variation in your system. So you may change those small s and big S, but then you will get a wrong result. The idea of that experiment that first you get like the ideal situation with the inventory policy. You just define the, let's say, ideal parameters for the inventory policies, which works perfectly without any stochastic things inside your supply chain. And then once you introduce this stochastic, like the demand or lead time or something else, then you measure that difference between like the ideal policy, let's say the ideal, and the actual one. You see, and that's exactly your safety stock. That's the idea behind that. So you actually may define any like inventory policy which you treat as an ideal one. And then that experiment will just measure that difference between the, let's say, the ideal one and the one which is actual, let's say it that way. Does it make sense? Okay, let's, oh, sorry, yeah.
Hi, I noticed your inventory policies were set for min-max. Does the safety stock experiment or estimation use MRP policy as well? Can it be run for MRP?
Not at that point. So currently it supports only regular policy and min-max policy.
You see,
Are there plans to?
yeah, MRP is a bit different because of, you see, MRP already based on some demand forecast. So it's already taken into account that demand will be changed somehow, right? And you will adjust how much you order. So that's why, I mean, because you already just implemented there some logic which is related to the demand, then that safety stock problem, it's different one. We even don't tell about like the safety stock here. We probably talk about, we talk more about the forecast mistake, the forecast error, right, with that. So you can do that estimation, but not with that experiment. And so, because it's based on some other assumptions.
Got a question over here.
Oh, yeah.
Okay, could we use another probabilistic distribution when you choose the variability?
Oh, yeah, sure.
Is it possible to implement an empirical distribution or something like that?
Yeah, sorry, probably you're the best person to answer that question.
So yeah, if we switch to any like numerical field, we can choose a number of distributions. Now we have only the most used ones here, but we'll include like all the distributions supported in AnyLogic, which is more than 100. Yeah. And of course, you can define specific distribution for like specific customer demand. So you do not have to necessarily have the same distribution for all the demand or transportation time or production time. So you can specify different distributions with different parameters in different places of your scenario.
Okay, more questions? Okay, let's continue then. Yeah, the next experiment we are going to do, this is to estimate the cache dynamics. Because one of the things which is important when you run a supply chain or business, so you want to understand when and how much cash you will have actually to pay your expenses. And so the dynamic simulation is a unique approach to do that kind of calculations. So what do we assume here? So we have the suppliers and we have to pay them within 20 days with down payment of 20%. Our customers pay us within 30 days. And we start operations with 1 million balance and interest rate is 8%. So in case we don't have money, we just get this money from the bank.
We get loans, yeah.
So let's show you the next slide. Yeah, again, that's the just visual representation of what I just said. So this is the supply chain. So we have like a cash account. So, and from that cash account, we have to pay all the operational cost of our supply chain. So then we have customers with the payment terms here. Those payment terms actually form account payable. And once
receivable.
Oh?
Account receivable.
Oh, yes, sorry, yeah, account receivables. Once we get paid, so we just add that amount, yeah, to our cash account. But at the same time, we also have to pay to our suppliers. So we have account payable. We also have payment terms with our suppliers. And, well, we pay them according to those payment terms we defined. Then, if you don't have money, we just go to the bank, get the loan, and return loan plus interest. So that's just, again, the simple explanation of what it does. I mean, this cache to serve experiment. So let's continue.
So again, I will create a copy of experiment just to keep track of changes. And I will name it cache to serve. So as Timothy said, we need additional information about payment terms and accounts in our scenario. So that is what I'm going to add. And I will create a cache account. And you can have separate accounts for parts of your network. So you define account and facilities that use that account or share that account. In our case, we'll have just one account, so all the sites will use that account, and we'll have 1 million as initial cash, and our interest rate will be 8% annually. So that is our account, and we also have to define payment terms. And again, each pair of seller and buyer can have their own payment terms. And again, for simplicity, for this presentation, we'll have just 2 lines here. The first will refer to our sales to end customers, and deferment period will be 30 days. The second line will be our relations with supplier. So when we buy from supplier, our factory buys raw materials from supplier. We have a 20-day deferment period, and we also have down payment of 20%. So actually that is enough to define cash flow in our model, but we also want to measure it, right? So I will go to dashboard and I create a new tab called cache to serve. And I will add cache to serve statistics. So dynamics of account payable and account receivable. I will also add our cash dynamics together with loan plus interest and interest separately. And again, I will make it as line. And as a third statistics, I will add total interest paid, because that's where we lose money, right? We take loan and then we return it with certain interest amount. So I run the model. And we see the dynamics. So from this chart, we see that our kind of return of investments is kind of 45 days. So we go down like 25 millions like this. So we compensate that with loan, and we pay off interest, and the total interest value is pretty small because it's only 45 days period, right? It's $132,000 US. And on this chart, we see dynamics of account payable and account receivable. So since our payment terms are only 20 days, that amount is much less than, and we have down payment of 20%. So our account payable is much less than account receivable from our customers who have 30 days deferment period.
So that model is pretty simple. It's only we have just one product, so, and dynamics of that cash dynamics probably was obvious. But once you have many products, you have different payment terms for different products, different payment terms to different suppliers you have. That picture just have like the problem just, I mean, the complexity of that problem just grows exponentially. I mean, if you want to estimate, to analyze what should be the payment terms with your suppliers, with your customers, how much cash you will have, that's actually, again, I would like to underline that the dynamic simulation is the only approach which allows you to do that kind of analysis or estimation. So, any question on that part? No? Could we switch back to the slides? So, you probably could think that we forget about marketing of our products. We are not. And while working on that scenario, we were sort of thinking, we thought that's okay, with all that done, we're almost ready to run our product, and actually how we will just negotiate that message, I mean, negotiate that, let's say, how we will just talk to potential customers that our product is real cool. Because this is a wireless banana phones, probably we would focus on the teenagers.
Ernie? Hey, Ern.
Oh, hi, Bert.
Yeah, hey, Ernie, do you know that you have a banana in your ear?
What was that, Bert?
I said you have a banana in your ear, Ernie. Bananas are food. They are to eat, not to put in your ear, Ernie.
What'd you say, Bert?
Will you just take that banana out of your ear?
I'm sorry, you'll have to speak a little louder, Bert. I can't hear you. I have a banana in my ear.
So with that said, so that's all with the workshop. So if you have any question, yeah, please let us know. We will be on the conference all the time, I mean, tomorrow and today. So again, you may just come to us if you have any just specific question about AnyLogistics. So thank you very much.
Thank you.